right, so how many of you have ever worked in object-oriented development languages? Whatever language that is. Okay, good. A lot of people. How many of you are currently working in JavaScript? Okay, now where's the Venn diagram between JavaScript and OO programmers doing OO in JavaScript? Well, that's interesting. So like everybody's doing object-oriented languages, everybody's doing JavaScript, hardly anybody's doing both together. So hopefully this will be an informative talk for you. So in object-oriented programming and in other language paradigms, we tend to talk about pillars and foundations and principles and things that we all build as the core of our system. And these tend to be things like polymorphism and inheritance and encapsulation, which are great foundations and great principles. But often what happens when we take these principles and values out of class-based static languages like C++ and C# and Java, and we try to apply them to a language like JavaScript, which is loosely typed and definitely not class-based, we end up creating, in our minds at the very least, the idea of mountains that we're trying to scale in order to get these object-oriented principles and foundations in place. And this tends to have two basic effects on the extremes, with a whole bunch of gray stuff in the middle, of course. But on one hand, you have the people that say, crap, I'm screwed. This is impossible. There's no way. You want me to free scale this mountain? I have never once even climbed a hill, let alone a mountain. And on the other hand, we have people that say, I got it, no worries. No, I've never done it before, but how hard can it be? I see these two guys doing it. They're a bunch of jokers, right? So we end up with all this stuff in between there, of course, but on these two extremes, we have kind of an unfortunate circumstance of opinions and code and stuff being thrown around, and it tends to lead people down the path of creating things that buckle under pressure. Stuff that just can't hold up to the weight of maintenance and heavy usage and all of the additions and changes that we have to make in our software, and people throw their hands up in the air and get really frustrated with object-oriented programming, and they just toss it out the window almost entirely. And that's a really sad thing to do, because there's a lot of great things you can do with object-oriented programming. But it's an unfortunate reality. It often does come crashing down around us, and we end up, just in really bad situations. The good news is, it doesn't really have to be that way. There are some simple things that we can do to get us past the mountains and get us to stable code that doesn't buckle under pressure like this, and allows us to build staircases up these mountains that we actually do have to climb, and allows us to iterate and build new staircases when the old ones are no longer useful, and allows us to find additional paths of getting things up and down the mountain as we need to. And there's a lot of good principles and a lot of good patterns and a lot of good practices out there in order to help people get down the path of writing good, solid code, pun intended, of course, including the solid software development principles. Now, for those that have not heard of SOLID before, this is an acronym of acronyms. It was assembled in, I think, the late 90s by Uncle Bob Martin, and it's a series of what I like to see as progressive principles and patterns that we can put together. I know you can look at each of these individually, but they actually do tend to play together really well one by one. So within the SOLID acronym, there are, of course, 5 individual acronyms. There's the single responsibility principle, which basically says that you shouldn't be putting all of these things together just because you can. You should know when and when not to. There's the open-closed principle, which says that we should be able to modify the way things are behaving without actually modifying that thing itself. Seems a little counterintuitive, but you'll find that you're already familiar with that. The Liskov substitution principle is all about substitution, taking one thing out and putting another thing in, and really gets down to the semantics of, are you sure that the clock radio duck is a real replacement for that mallard? The interface segregation principle. Now it says interface, but it is not talking about user interface, even though that is really the easiest way to understand this principle. Interface segregation principle is saying get really small, simple interfaces so that developers don't pull their hair out trying to figure out what you meant. And then the dependency inversion principle, which is all about abstraction, but more importantly, who owns the abstraction. All right, so we're going to dive into each of these individually. We're going to look at some analogies in the real world, which will hopefully make these principles a little more salient, a little more understandable for you guys. And then we're going to look at some code samples from a wide range of JavaScript, in addition to some idiosyncrasies that JavaScript has that makes these principles a little bit different when applied in this language compared to C++ and C# and Java, where they are more traditionally applied. All right, so first up we have the single responsibility principle. Now, a lot of people have been talking about SRP at the conference already. I've heard it mentioned several times. And a lot of people say, all right, single responsibility, everything should have one responsibility, one reason to exist, right? Well, the truth is that definition is slightly wrong. From one perspective, yeah, I totally agree with that. But the actual definition of the single responsibility principle is that everything should have one reason to change, not one reason to exist. And that perspective is tremendously important because it helps to take us, the right-brained engineers that want to overanalyze everything, and it puts us into the context of what we're actually building so that we can build the right thing and not necessarily the thing that we think is the most analytical way to break everything down into pieces. So what this really means is you, as a developer, designer, whatever it is that you do at your job, you need to understand, are you building a jet or are you building a jet? Understanding this difference is critical, because if you're building an actual jet engine or a simulator for a jet engine or a jet maintenance program, you're going to have a whole lot of regulations to go through. You're going to have a whole lot of engineering principles to think about. You have a lot of detail that you need to keep track of in order to model that actual jet engine correctly. But if you're building Legos or Play School toys or whatever it is, chances are you just need something that happens to look kind of like a jet, and maybe if it's a remote controlled device, you have go forward and go backward, and that's about it. So understanding what you're building is critical because it informs you of the responsibilities of each of these pieces. And when you know what the responsibilities are, you know why these things actually need to change and when they need to change as well. So we'll get into a little bit of code here and show some examples of this. So here I have some really basic Backbone stuff. If you've never seen Backbone before, don't worry about it. I'm not going to be showing Backbone the whole time. Just as one really simple example. So I have a Backbone view that is an employee info form. And a Backbone view manages some HTML elements, and it allows you to get information in and out and manipulate those elements. So this employee info form is the first of two steps in a workflow in order to create an org chart. So the employee info form lets me get email and info about the employee, and then there's the select manager form, which is the second step in the process, which allows me to say who the manager of that employee is. So when I click the next button, which I've got the callback handler right here, I gather data from this, and then I create a new employee object, and then I call select manager. And select manager creates a new select manager form, renders it, stuffs it into the DOM, and you get your nice little workflow wizard clicking that next button. So let me ask a question now. Does this code violate the single responsibility principle? Does it break that principle down and do bad things? Anybody want to venture a guess? Yeah. Yes? Yes? Well, if you said yes, you're maybe right. If you said no, you're also maybe right. The only viable answer to that question is it depends. And the reason that the only viable answer is it depends is because it truly does depend on what you're actually building and why. If this were a very small piece of a large system, and this was all it needs to do, and there is never any chance, or at least not in the foreseeable future, that it's going to do anything else, fine. I got no problem with this code. Sure, maybe you can analyze this code and see where it does bring too many responsibilities into one of these objects. But if it gets the job done and you don't need to maintain it, who cares? Get it done, move on. However, I think this code does break the single responsibility principle from the perspective of, okay, I built this code, and now I need to maintain it, and now I need to work with it a little more and add changes to it. All right, so I need to actually change the workflow of this code a little bit. But now I've run into a problem because I've got too many responsibilities in this employee info form. I need to see the workflow that's going on here and change the workflow. And asking me to do that is a little bit like sticking me in the middle of this forest and telling me to look around at all of the individual trees, find where I'm supposed to be going, and figure out how to get there, just by sticking me in the forest, nothing else, no maps, no anything else. When in reality, you need more than just the individual trees around you. You need more than the code that you're looking at. You need that high-level map to tell you, oh look, you're actually sitting right here where that nice little yellow tree in the middle of the screen is. And you need to get over here to this clearing, and then over there to that clearing, and then to the beach, and you need to get all these things done so that you don't get lost in the forest, and so that you're not doing the wrong thing. You need that high-level perspective and understanding so that you know what you're actually supposed to be doing. So in the single responsibility principle, if I'm coming along to this code and I see, oh, hey, look, I need to add more to the workflow. Well, crap. I have too many reasons to change this employee info form because the employee info form contains not only the employee info, but also the workflow to get to the next step and knowledge about what that next step actually is, being the select manager form there at the bottom of the screen. So what I might want to do in this case, if I'm going to be adding steps, is first extract this out into something high level to give me a map, to give me a flow chart in code, so that I can actually say, I'm going to start with add new employee. And then I'm going to, when the add new employee stuff is done, I'm going to call select manager. And once select manager is done, then I'm going to go ahead and save the employee. Now that I've saved the employee, so now I have a much higher level map that I can work with. And this is important in this case because the responsibilities were, the reasons to change were, change the workflow, add a new step, get something else done in here. So now that I've extracted this code, this workflow object, this org chart, has one reason to change. You need to change the workflow, you change this object. You need to change what information is gathered or how it's gathered for the individual employee, well, you change the employee info form. Now we're starting to see separation of those responsibilities and one individual reason to change that code. So up next, we have the open-close principle. Now the open-close principle says that things in code, whether those are functions or objects or modules or whatever they are open to extension and closed to modification. That is, we can change the behavior of the existing code without changing the existing code. Sounds a little wishy-washy, maybe counterintuitive, like what the crap is this guy talking about, right? Well, it is a little wishy-washy at first, until you come to realize, okay, it's not just open or closed. We're not talking about one thing here. We're actually talking about multiple things here. We're talking about the code that is currently running, and then talking about plugins or extensions. Now, who here has ever seen a plugin or extension in real life? Every one of you has a tablet, a phone, a USB mic, a hard drive, a something that has this little male USB end with another computer or laptop or something that has a female USB end, and you plug them together, and your computer suddenly does new things. You've changed the behavior, at least the capabilities for behavior of that computer without tearing apart the computer to put new hardware in place. And the exact same thing is true for code. We can change behavior in code by providing extension points. Now, I'm not just talking about large-scale frameworks that have extension points that third-party developers can come along and modify. Even within your individual applications, we can put extension points in place to make your lives easier as developers. So a switch statement is a good place to look for an implementation of the open-close principle. I've got here an employee object, I've got an action, I've got a switch, it looks at the value of the action and decides what code to run based on that. Pretty simple stuff. Now, if I want to modify the behavior of these actions, what do I have to do? Well, I have to come modify the switch statement. If I want to add a new switch statement for a new action, okay, so this code is open to extension, open to change, but it requires me to change the actual code. And that's a violation of the second half of the open-close principle. Open to extension, closed to modification. So instead of using a switch statement, I might want to do something else like a registry or a dictionary or a hash table or a key value pair or whatever you want to call it. I want to register the show employee function with the view action. I want to register the edit employee function with the edit action. And when it comes time to actually get the action name, then I can retrieve the action itself by that name and get the employee that I need to work with and then execute that individual action. So this code, it looks a little bit smaller. In truth, I added another registry object, so the code is not technically smaller. There's a little bit more over here, but that's fairly simple code. But the more important thing is that we now have code that conforms to the open-close principle. We can extend this code with additional actions at some later point in time. We can add new actions anywhere we want as long as we have access to that registry. And there's some examples that I have in here using AMD and require.js where you can set up some registries and look at these, and I'll have this code posted later so that you can take a look at it. But the open-close principle is all about creating code that can be plugged in and have new stuff added to it instead of having to change the code that's already there. So we start to get an idea of abstractions at this point. And the good news about the open-close principle is that it also tends to lead you down the path of single responsibilities because now you need individual things to implement all of the new behaviors that you need. So we start seeing how these things add on top of each other a little bit. So Liskov substitution. This is named after Barbara Liskov, and it's got this nice, beautiful mathematical formula that I hate reading and looking at because I'm not a mathematician and it's not fun to try and decipher. So I like a more simplified definition of the Liskov substitution principle, which tells us that derived things must be substitutable for the base thing that they come from. So this again is all about abstraction. And a lot of people, myself included, like to say that Liskov substitution principle is a more focused version of the open-closed principle because it allows us to take the abstractions that we built for open-closed and say, now that we have an abstraction, an API that we need to conform to, we know the size and shape of that API, but now we also need to deal with the semantics of that API. And semantics are tremendously important because, as my friend Sharon Chikeli likes to say, semantics will continue to be important until we learn how to communicate in something other than language. Because everything we do, everything we say is semantic. And if it's not, you're not really going to understand what's going on. All right, so the size and shape of the API is the first indicator of whether or not we've broken the Liskov substitution principle. We can look at an abstraction, an API, an interface, whatever it is, and we can say, oh, look, 2 prongs, I got this. And then, oh, crap, I'm trying to put a square adapter into a round hole. This is not going to work. It's usually pretty easy to see where API incompatibility happens because you can just look at the API and the documentation and see that it's not going to work. Where it gets more subtle and more difficult is when we start talking about the semantics of the API or abstraction. So the best way to understand this is yet another analogy: squares and rectangles. In math, all squares are rectangles, right? Not all rectangles are squares. Well, okay, all squares are rectangles. So a square is a rectangle. Let's go ahead and look at what that would be like in code. So here I have a rectangle. Rectangle has a constructor function, it has a set height method, a set width method, and an area. So the area, of course, is height times width for a rectangle. Down below, I have a test. I'm describing the area of a rectangle, setting the height and width, and expecting that the area is the height times the width. We're good to go. I pass in a new rectangle to my test function. Everything passes. No problem. All right. So now I have a square. And like I said, a square is a rectangle. So let's use the noun-verb analysis that we've all grown up with in object-oriented programming and say is a means inheritance. So I'm going to create a square constructor function, and I'm going to have the square inherit from rectangle. And this is prototypal inheritance in JavaScript. Don't worry about that if you've not seen it before. This is just inheritance. Except there's a problem. In a rectangle, when I call set height and set width, it sets those individual attributes. But in a square, height and width have to be the same thing. Otherwise, it is not semantically a square. So, okay, I'll have set height and set width, both call set size, and then set size will make sure that height and width are always the same thing. Okay, easy enough. I still have the semantics of a rectangle, and now I have the semantics of a square. Except, look at our test. Our test is trying to take this rectangle, set the height and width, and assert that the area is 20, only now we're passing in a square. So the result of this area on this object is not going to be 20, it's going to be 25. And the only way we could get 20 is by using the square root of 20, which is like 4 point some odd crazy number that I can never remember. You're not going to get the same semantics out of a square and a rectangle in code in this particular abstraction, which leads me to believe that we have the wrong abstraction. So this is where semantics really become important in Liskov substitution. If you have two things that you're trying to replace each other with, but they are incompatible for API reasons and behavior reasons, you probably have the wrong abstraction. So in this case, instead of a rectangle as the base, what we really want is something that has area, because that's the commonality between a rectangle and a square in our test. What has an area? Any given shape. Circles, triangles, rectangles, squares, trapezoids, whatever they are, they all have areas. So we can take an area and we can build that, and we can have a rectangle inherit from area, and we can set the height and width, and we can have area on the rectangle return height times width, and then we can have a square that doesn't have height and width, just has size. Semantic differences here, creating a new API. And then the area of the square just returns the size. And now our test for area of a rectangle and area of a square can also be split apart so that they are both semantically meaningful. Now this does bring up a little oddity in JavaScript. This code does not look very JavaScript-y, quite honestly. It looks very Java-y or C#-y, except it just happens to be using prototypes instead of class-based inheritance. There's a problem in JavaScript in that we don't have strict interface constructs, so we don't really need base classes with empty implementations. But I'm going to get back to that in a couple of minutes here. Before I get to that, I want to talk about one of my other projects, Marionette.js. It's an application framework on top of Backbone, and it gives scalability to Backbone with a whole bunch of really neat things. And one of the things that's in there is the idea of a region. Now, a Backbone view manages HTML elements. A Marionette region manages placing a Backbone view in the visible DOM or removing it from the DOM. So that way your views never have to worry about where it's actually being displayed, separate those concerns, and all that good stuff. But in this code, there's a small problem here. Long time ago, when I first built this region, there was no built-in method in a Backbone view to close or dispose of that view. So I built a base Marionette view that had a close method. And I said, all right, if you pass in a Marionette view when you're trying to close this region, I will look for a close method because I'm also going to accept the standard Backbone view. So if there is a close method, I'll go ahead and call it, and that will close things. And then a little while later, Backbone came along and said, hey, we need a way to close our views. Except instead of calling it close, they called it remove. So now I have an API incompatibility. So now I had to go into my Marionette region object and add a special case. Are you dealing with a Marionette view that has a close method or a Backbone view that has a remove method? And worse yet, I made the marionette base view call backbones remove. So I have to say, if there is a view.close, call that. Otherwise, call remove. Don't call them both if both of them exist. This is actually a violation of the Liskov substitution principle. I've broken the semantics and the size and shape of the API here. There are some semantic differences between my close and backbone's remove, which is why I also call remove from my close. Now, this actually is a useful violation, which is another really important point. Just because you're violating a principle doesn't mean you're wrong. There are times when it is the right thing to do so that you can create flexibility inside of your systems, and this is one of those times. All right, so the interface segregation principle. Make fine-grained interfaces that are client-specific. Again, this is not talking about the user interface, although the user interface is the easiest way to understand that. How many of you have ever been frustrated to death by a multifunction printer, copier, scanner, faxer, dog chewer, coffee maker, etc.? These things are horrible. I hate them. I just want a photocopy button. I don't want to have to deal with the 50 buttons that are on this panel and then the literally unlimited potential for more buttons inside of a touch screen. Dumbest thing ever added to a multifunction device of any kind, because it's impossible to find what you want unless you're apt at using the thing from doing it all day long. What I really want is the easy way out. Just give me a photocopy button. Just give me a print button. Just give me a call my mom and order a cheeseburger button. Whatever the button is, I just want that one button to make it nice and easy for me. Well, think about this from a code perspective as well. When I'm dealing with code and writing APIs, I also want something super duper easy. I don't want to have to deal with 50 different API methods in order to get something done. I want something very narrow, very simple, very clean, so that I can just press the one button, call the one method, and get all of the power and capability out of your library. Now, the problem that we run into, which I started alluding to a moment ago, is that we don't have explicit interfaces in JavaScript. There's no interface construct. And when we do inheritance, there's still no explicit interface definition on that object. We can modify our base object or the new object instance anytime we want. We can add methods, we can add values, we can delete methods and attributes. We can do whatever we want with those objects. So a whole lot of people that are a whole lot smarter than me came up with the idea of protocols. And Jim Weirich talked about this in his Solid Ruby talk in 2009. And the idea of a protocol in a dynamic language like Ruby or JavaScript is more focused around documentation than it is language constructs. We are declaring a protocol for these things to talk to each other, rather than having an explicit interface construct like in C#, which is essentially a contract that says, I'm a lawyer, you will do this. This is a handshake. This is, hey, let's do these things together. Let's get this done. Let's make it work. So we have protocols. But a protocol has to be documented well. Otherwise, nobody's going to know what methods and attributes are needed when they pass one object into your stuff. So what does this look like in code? And it's the C#. So back to the rectangle and square problem. The good news is we've actually already solved this problem with the rectangles and squares. If I go back to the original rectangle and square, we can see that I've created a little bit of a mess in the API for the square at this point. I've got the square inheriting from rectangle. The rectangle had set height and set width, but I really wanted a set size, so I just tacked on this extra method. Because the things that use squares know about this method, right? Well, now I've got too many interfaces going on here. I've got too many possibilities. I've got questions. When I see a square and I see that it has this set height and set width and a set size, which one do I call when? I have no idea, because there's too many things going on, too many options and possibilities. So this is breaking the interface segregation principle, while it also broke Liskov's substitution principle. And when we got down to cleaning this up, and we separated out the rectangle from the square, we also, at the same time, cleaned up the interface. Because now I have a rectangle with an area, a height, and a width, and I have a square with an area and a set size instead of a set height and set width. Well, the protocol that we're dealing with is that of a shape. We're not dealing with square or rectangle, we're dealing with shape. And the shape protocol in the documentation that we magically have somewhere else, not on the screen, says that you must provide an area function that returns some value to say how big this thing actually is. So that's the interface segregation principle, giving me the ability to have individual methods and attributes that are focused on the one thing that I'm trying to do, instead of an all-encompassing, you can do anything you want with this. Just give me something focused. Make it easy for me to use your code and your library, because I don't have time to think about what you were thinking through when you built that crazy interface. So last up, we have dependency inversion. And there's two parts to dependency inversion. There's abstraction and there's ownership of the abstraction. And we're going to talk about each of these individually. So in abstraction, we say depend on abstractions, not on concrete things. What this really comes down to is the problem of the ripple effect. If we're depending on concrete things, our ripple is going to be too large. And what I mean by that is when we have dependencies on concrete things, when one object directly instantiates another object, every time we change the object that we depend on, we have a ripple. Now we have to change the code, potentially have to change the code that's using that object. Too many ripples is a bad thing. Not enough ripples is also a bad thing. We don't want our code to be like lava. We don't want it to have the appearance of flow and the appearance of the ability to morph and change, but then have it in reality get solidified into stone that requires a jackhammer and dynamite in order to change it later on. That just puts us in as bad or worse of a situation than we were already in. So in our code, when we look at abstractions, and we look at concrete objects, how many of you guys have ever built, guys or girls, sorry, I keep saying guys, how many of you have ever built an object with a constructor that directly creates another object inside of it and holds on to it for later use? I mean, I do that all the time. It's a pretty common thing to do, right? You say, okay, my type constructor function, you're going to hold on to something, and later on, you're going to use something, and then I'm going to pass parameters into the parent function, and all is good until suddenly something changes for some reason unrelated to my type. So now I have a new constructor parameter. I need to come in here and add this parameter to this constructor function. Well, there's my ripple. I changed something which forced me to change my type. When in reality, my type shouldn't have to know about that, shouldn't care about that at all. So when we talk about depending on abstractions, what we're really saying is just pass the object in as a parameter to the constructor. It's pretty simple. Abstractions and dependency in inversion principle, from an abstraction perspective, are typically just parameters passed into methods or constructor functions. So now, when something changes, and oh look, I no longer need that new parameter there, I'm going to change that. Okay, I changed something. I didn't have to touch my type anymore. I reduced the amount of ripple in my code. There was no longer a need for me to change too many things. Sure, I still had to change the code that was using something or instantiating something, but I didn't have to change the my type object. So that's abstraction in dependency inversion, which brings us to the second part of dependency inversion. And this is where most people fall flat on their face with dependency inversion. They get done with the abstraction part and they go, yay, I'm done, I got inverted dependencies, and I'm just going to ignore the most important half of this because it's too hard to think about, or they just don't know about it, or whatever it is. So the second half of dependency inversion is that detail depends on policy. Low-level implementation and actually getting work done depends on high-level concepts that orchestrate how things are supposed to be done. You ever used a lock and key? Have you ever picked up a random key off of the counter, walked over to a lock and said, this key doesn't fit. I'm going to disassemble this lock and reconfigure it to match the pins on the key that I just found, put it back together, and then open the lock. I mean, it's ridiculous, right? That's not how keys and locks work. Because the key does not own the pattern of bumps and ridges. The lock owns the pattern of bumps and ridges. And we have to find something that satisfies those dependencies, that dependency of that shape, in order to unlock or lock that thing. So in code, what this comes down to is again, again, my type. Only in this case, we're going to start looking at protocols again instead of explicit interfaces and abstractions. Because when we look at this code, we see, okay, hey, my type depends on something. We've already extracted something into a parameter that we're passing in. But what happens if something has a method name change? Instead of do that, it's now do this. Well, that change to something had that same ripple effect that we were trying to get rid of. We don't want my type to change just because something changes. So instead of depending on a parameter that's named after the type or object that is passed into it, we really want to depend on, I keep pulling up the wrong one. We really want to depend on a named protocol. We want to have a protocol that says, these are the things that I'm going to do. This is how you're going to communicate with me, and I've documented this protocol over here, and this is what you must do in order for me to use you so that I can call your methods. So now when we look at this code, we see that the parameter passed into my type is no longer called something, it's now called doer. It does stuff. And we hang on to doer, and later on, we call this method on doer like we've always been doing, and we pass some values into it that we need to. And now we have something, and something is supposed to be our implementation of that protocol. So the something object must conform to the doer protocol. If it doesn't, it's going to blow up. We're going to get errors, we're going to have problems. Going back to semantics in Liskov substitution, we better make sure that we are semantically meaningful as well. But again, protocols don't exist as a construct in JavaScript. They exist as a concept and typically outlined with documentation. You better be documenting these protocols that your objects expect. Otherwise, people aren't going to know what to do. And the reason that we talk about protocols and we talk about having my type depend on a protocol is again coming back to ripples. My type owns the doer protocol. It is the only thing that can say this protocol must change, must do something different, because it owns that protocol. And the reason it owns that protocol is because we want to prevent something from rippling changes into my type once again. If the doer protocol has to change because there's too many parameters in here, or not enough parameters, or whatever the case may be, the doer protocol will change only because my type says it must change in order for my type to do its job. So now we do have a ripple still. Since my type said this protocol must change, something must change in order to conform to that new protocol. But that's okay. This ripple is perfectly fine. This is a downward ripple into the detail of the system versus changing something and then forcing my type to change being an upward and outward ripple. The doer protocol is policy. Something is detail. Detail depends on policy. not the other way around. So that really is the most important aspect of the dependency inversion principle. It's not just that we are turning things into abstractions and passing in parameters. It's that we have explicit ownership of these abstractions in order to keep our code from exploding with changes all over the place. All right, so what did we really gain by looking at this very high-level overview of these principles? Is there anything that is a drawback to this as well? And quite frankly, I think there are some drawbacks to this. I've also shown some points, like in the Liskov substitution, where the principle was violated, but I did it on purpose because it made the code more robust and more capable. So if you have large monolithic chunks of code in your system, the SOLID principles are going to help you break these things down into individual pieces. Now, I'll tell you right up front, you will not reduce complexity in your system by breaking large things down into small things. Not one single bit. Chances are you're going to increase the complexity. But that's okay, because once you have things broken down into smaller pieces, you can create natural relationships in between those pieces. You can start seeing how these things fit together in the bigger picture. And better yet, you can start naming those things. When I pick up this bottle, I don't pick up a series of hydrocarbons strung together in a certain configuration and expanded with gas in order to create a shape and filled with. I don't think about those implementation details. I think about the abstraction of, I have a bottle of Gatorade in front of me. I'm thirsty. I want to drink it. We as human beings do not think in details. We think in abstractions. Creating named abstractions that are meaningful in our system is tremendously important. It allows us to group small things together into larger concepts so that we can reason about a group of larger concepts instead of having to reason about all of the individual implementation details all the time. So that's what the SOLID principles give us. Of course, the SOLID principles aren't the only principles that we need to look at. They're just one set of principles that can help get us down the path. But in the end, the SOLID principles will help us get away from the burning Jenga game that our software often is, trying to wiggle one piece out and having it come crashing down, setting the whole house on fire. And they really will give us fluid code. Code that channels itself around the landscape, around the domain that we're dealing with, around the issues and around the problems that we face. Code that knows how to react and respond to the changing environment all the time. So that's pretty much it. I hope you enjoyed the talk. My name is Derek Bailey, by the way. I work for Kendo UI, and we have a booth right outside this door, so be sure to stop by and check out what we're all about. And here's a little bit of info about me. Please come ask questions. I got a little bit of time here for some questions, or you can always email me or find me on Twitter. Thank you. I think someone had a question over here. Yeah, I'll have the slides online later. I also recorded all of this, and I'm going to post the entire video to YouTube. Hopefully if the audio came out. Yeah, the code will be up there too.